The midterm for this course covers from chapter 2 to chapter 5. And for the midterm, there will be about 10 to 12 questions, and each question is very similar to what you have done in your assignments and the examples I've shown in the lecture notes. So in this video, I will quickly go over the key points from chapter 2 to chapter 5 for you to review. So for chapter 2, first, we talk about the ingredients of a mathematical model. So here we talk about the three concepts: variable constant and a parameter. So this is just like a background for you to know. And then we talk about the real number system. And so you should be able to know what's a rational number and what's an irrational number and what's a relationship. And also the sets. This is our key point in chapter 2. So you should be able to know the definition of a set and the relationship. So for example, if I give you two sets, so you should know that which one is a subset of another one, or are they equal to each other, or are they the subsets or the proper subsets of each other, or the disjoint. Right. And also for the operations, this is also important because I may give you several sets and to ask you to find out the sets of the unions of any of the two sets or the intersection of two or three sets. So you should be able to know the answer from the operation of the sets. And here are the laws of operations. So yeah, laws of set operations. Yeah, it's just something that you need to know. Maybe not for the midterm. So for the functions, you need to know what's a function, right? What's the definition of a function? So the most important thing here is that the independent variable x should uniquely determine y, but y does not need to uniquely determine x. So for every x, there has to be one and only one y that is corresponding to the x. But for one y value, there may be many x values that's corresponding to the y value. So x should uniquely determine the y, but not the reverse. Right? So that's the most important one. Okay. And also for the domain and the range, domain is the values that x can take, and the range is the values that y can take. Right? But the value of y will depend on the value of x. Right? The relationship between x and y is the function here, for example, the cost function here. So if I give you the domain of the x, you need to be able to find out the range of y, right? From the function I give you in the problem. So this is chapter 2. And for chapter 3, so first we talk about the linear market equilibrium model. So for the linear model, we have the demand and supply curve. So both of them are linear. And we have an equilibrium condition, QD equals to QS. And then you should be able to use the three functions I give you to find out the equilibrium quantity and the price, P star and Q star. So for linear equations, it's very simple, actually. Just let Q equals to QD and QS, so all the Q's are equal to each other. And to find out the P first, and then you plug in the P star to any of the Q function to find out the Q star. Right, so this is the like linear one. And for the non-linear model, we talk about the quadratic form here. So for the quadratic form, everything is similar. We let QD equals to QS, and then we let the two functions, including P, equal to each other. And then we find out the quadratic function of P. So in order to solve the quadratic functions, we need to use the quadratic formula here. Right. So use the quadratic formula to find out the two roots of the function. So it's x1 star and x2 star. But if it's like a applied function, sorry, if the problem is a applied problem, so you may solve for the price, right, p star, and you need to know that the price should be positive. So you have to eliminate the negative price. Otherwise, you only get partial credit. So you have to eliminate the negatives value for the p star and to only include the positive ones left. And then use the positive p star to calculate the q star. Okay. And for the higher degree polynomial equations, the most important thing here is the three theorem. Actually, the first two theorems, right, are the most important one because you need to use them to find out the rational roots, right, or the integer roots, right. For the theorem one, if this is a polynomial equation and the coefficient of the highest order x to the n is 1, right? So if it's kind of this form, so you can find out the integer roots by checking if the divisor of a0 meets this equation. Right, and for the theorem 2, it's like a generalization to theorem 1. It doesn't, for the highest order x to the n, the coefficient is an now. It doesn't have to be 1. So this is like a generalization of theorem 1. And here we want to find out all the rational roots, right, including the integer roots for theorem 1. So for all the rational roots, R over S, so R should be a divisor of the constant term, A0, and S should be a divisor of an, the coefficient of the highest order. And then you find out, first you find out the pool of R, and then you find out the pool for the S, and then you find out all the potential values that R over S can take. And then you check one by one if these numbers will satisfy, or if these roots will satisfy this equation. So if any one of them will satisfy the equation, then it is a rational root for the equation. Right. And for the theorem 3, it's very easy to understand. You just plug in x equals to 1 to the equation to find if the left-hand side equals to 0. Right. Okay, so this is chapter 3. And chapter 4 and chapter 5 about matrix algebra. So first you need to know what's a matrix. And so here I may give you a equation system like this. Right, so this is called equation system. So from the equation system, you should be able to write out what is the coefficient matrix A, what is a variable vector X, and what's a constant term D, right? So from the m equations I give you, you should be able to extract the A, X, and D matrices. So this is the first job. Okay. And also, I may ask you to find out if the coefficient A has inverse or not. And okay, so we can write the equation system like AX equals to D. So we'll talk about the matrix A. We'll talk a lot of things about the coefficient matrix A a lot in the following. But before that, we'll talk about the matrix operations, like the addition and the subtraction of matrices. So this is just something I think is easy to understand. You just need to add the corresponding pairs together to find out the new matrix. And for the subtraction, you subtract from the corresponding pairs and to find out the result. And for scalar multiplication, you just multiply the scalar with all the elements in the matrix. So this is your new matrix. And the most complicated is the multiplication of matrices. So here I give you an abstract example. So first, for A and B, first you need to find out if they are conformable to do the multiplication. So if they are conformable, that means that the number of columns of A equals to the number of rows of B, right? So if they're conformable, then you need to find out the dimension of the resulting matrix A and B, AB. Right? So the dimension is the number of rows of A and the number of columns of B. So in this example, the C is of dimension 2 by 4. Okay, then you write out the 8 elements of matrix C. So for each of the element, you take the corresponding rows and a column from the first matrix and the second matrix and do the inner product. So for example, for C11, you need to take the first row of A and the first column of B, and then you multiply the corresponding elements together and then add them together, like here, to find out the C11. And for all the 8 elements of the C matrix, you do the same thing and to find out the 8 numbers of matrix C elements. So this is a product of A and B. So the product, the multiplication of matrices are the most complicated, but you have to know how to find out the product. Right. And then it's a vector operations. So just like a so you can think about the vectors as matrices, but with only one row or one column. And so the operations are exactly the same. I mean, yeah, for the multiplications, we follow the same rule as before. And we talk about the linear dependence. So we talk about linear dependence allowed in chapter 5. So here is just like a basic introduction to linear dependence. And then we have some of the laws, right, like cumulative law, associative law. And the most important thing here is the matrix multiplication is not commutative. So A times B is not equal to B times A, right? Because we're doing the matrix multiplication, it's not like the number algebra. So the multiplication of two matrices are much more complicated. So A times B is totally different from B times A. Okay. And then we introduce the identity matrices and norm matrices. So for identity matrices, you can think of that as number 1 in the number algebra. So A times any matrix is the matrix itself. Right? No matter how you change the order, it will not change the result. Okay. And for the norm matrices, it's kind of like the number 0 in number algebra. So the norm matrices times any matrix equals to the norm matrices. So A times O equals to O itself. But the dimension may change, right? This O is different from this O because it will change the dimension. But all of the O's will belong to the norm matrices. Okay. And then we talk about the transposes and inverses. So transpose just means that the rows and columns of a matrix are interchanged. So you should be able to find out the transpose if I give you any kind of matrices. Okay. And for the inverses, we'll talk about how to calculate the inverse matrix in chapter 5. And for the inverses, I think you need to know how to find out the inverses and what's the properties of the inverse matrix. Right, so we have some of the properties here and here. Okay, this is chapter 4. And for chapter 5, first is a background about necessary and sufficient conditions. So you need to know what is a necessary condition and also sufficient condition. And then for non-singularity, there are two conditions. So first is squareness, right? That means that the matrix has to be a square matrix. And then the rows or columns of the matrix are linearly independent. So only a matrix that meets both of the conditions will the matrix be non-singularity. And non-singularity just means that the inverse of the matrix exists, right? We want to find out the inverse of the matrix because we want to solve the equation system here. We want to solve the x. In order to solve the x, we have to know the inverse of the coefficient matrix. So that's why we'll talk about how to find out the inverse and how to check if the matrix has inverse in chapter 5. Okay. So and then we talk about what is a linear row independence, and we said that okay, if there are like a linear relationship between any of the two rows or two columns of the matrix, then it's said to be linearly dependent. Okay, and then we said that okay, to find out the number of rows that are independent, we can use the rank of a matrix to do that. And actually, the rank of the matrix can be used to check whether or not the matrix A is non-singularity or not. So to find the rank of the matrix, we need to transform the matrix A into echelon matrix by the 3 elementary row operations. Right, so we have 3 kind of elementary row operations here, and you can freely use any one of them to change the matrix, to change the original coefficient matrix A into the echelon matrix. So echelon matrix just means that here. Echelon matrix means that the first element here should be 1. And then for the second row, the first element has to be 0. Or the first non-zero entry, we call that 1, and just number 1, should be to the right of the previous row. So it's called echelon. And if we have a row, the odd elements are 0, like A2 here, we move this kind of row to the bottom of the matrix. And the number of the non-zero rows is called the rank of the matrix. Okay, so we have like several steps to find out the echelon matrix. But the basic idea is to change the original matrix here, A1, to the form A5, right, using the elementary row operations. And the rank of the matrix A is just the number of non-zero rows in the echelon matrix. So here for A5, for example, the rank of the matrix is 2, right? Because there are 2 non-zero rows. And the matrix A is called a full rank. I think I didn't write it here. So it's called a full rank if the rank of the A equals to the total number of rows of A. Right, so here the total number of rows of A is 3, but the rank is 2. It's less than 3. So we say that A5, the matrix, is not full rank. And if the matrix is not full rank, we say that the matrix is singular, or the matrix has no inverse matrix. So only full rank matrices have inverse matrix, or only full rank matrices are called non-singularity matrices. So the rank of the matrix can be used to find out if a matrix is non-singular or not. So its function, the rank of a matrix has the same function as the determinant, right? We'll talk about that later on. So both of the determinant and rank can be used to check if the matrix has inverse or not. So here we talk about the determinants, right? So determinants is just a number that's associated with a matrix. So to calculate the determinants, for the 1-by-1 matrix, the determinant is just the element itself, right? The only element itself. For the 2-by-2 matrix, we have the rule to calculate the determinant here. And for the third order or higher order determinant, we use the Laplace expansion. So we first choose a row or a column to expand. And then we find out the cofactors, right? Cij, the cofactors for each of the elements you choose. So for example, if you want to expand from the first row, then for example, it's a 3-by-3 matrix, and you choose to expand from the first row. So for the 3 elements in the first row, each element has a corresponding cofactor. And you need to find out the cofactor of all the 3 elements in the first row. And then the formula to find out the determinant is here, right? So the first element times its cofactor plus the second element times the cofactor plus the third element times the cofactor. Right, so this is the formula to find out the third order determinant. And the cofactor Cij here is closely related to the minor of the element. The only difference between the cofactor and the minor is that the cofactor has a sign before the minor. The sign is determined by the summation of I and j. Right? If I plus j is even, then the cofactor is equal to the minor. But if I plus j is odd, then the cofactor it has a negative sign before the mij. So that's a relationship. Okay, so here we have a lot of examples showing how to calculate the determinant. And then there are 5 properties of determinants. So first, if you interchange the rows and columns, or if you take the transpose of the original matrix, the determinant doesn't change. And second, if you interchange any 2 rows once, right, any 2 rows or 2 columns once, the determinant will alter the sign, but with the same numerical value. Okay, and for the 3, the multiplication of any 1 row or column by any of the scalar will change the determinant of k-fold. Right, so if you multiply k to all the row numbers for the first row, for example, then the determinant will change k times. But if you multiply k for 2 rows here, 2 rows, then it will change the determinant by k squared. Right? And you need to know the difference between k times a matrix and k times a determinant. So k times a matrix means you multiply k to all the elements in the matrix. But k times the determinant means you change only 1 row or 1 column here. multiplying k to all the elements in the one row or one column. And fourth, an addition or subtraction of a multiple of any row or column to another one will not change the determinant. So here, if we see this complex determinant, we can simplify this by multiplying k for the first row and then subtract it from the second row. So we can simplify the second row, right, to A, B, C, and D. So in this case, the computation will be much easier than we calculate the original determinant. So property 5, if one row or column is a multiple of another, the value of the determinant will be 0. So property 5 is just like it's similar to property 4, right? You can use property 4 to find actually you can change the first row, for example, here to 0, and you can change the first column to 0. So determinant has to be 0. Right? So that from property 5, we know that if the two rows or two columns are linearly related to it or linearly dependent of each other, then the determinant is 0. And this matrix is not full rank, and the matrix has no inverse matrix, and it's not non-singularity. Okay. So to determine non-singularity, we can use the rank of a matrix to find that, or you can use the determinant to find that. You can check if the determinant of a matrix is not 0. Right? If the determinant is not 0, then A is called non-singular and A inverse exists, and we can find a unique solution X star for the equation system. So this is the criteria for us to find a non-singularity here. Okay. And then the last, we talk about an example here. And the last one, we talk about how to find the inverse matrix. Right, so basically, there are 4 steps that we should take. Right, so I didn't talk about how to prove this, but it's a little bit complicated. So I just talk about the 4 steps you need to do to find an inverse matrix. Not too much about that, because it will be too complicated. Okay, so first step, you need to find the determinant of the matrix. And then second, you need to find all the cofactors of all the elements of the matrix. So this step takes most of the time. Right, so we call this matrix C the cofactor matrix. And each element in the cofactor matrix is just the cofactor of the corresponding element in the matrix A. So Cij is just the cofactor of Aij, right? The same location. And then we take the transpose of C, and we call this adjoint of A. And then finally, we divide the adjoint of A by the determinant of A. And so the result is called the A inverse. But it takes a lot of time to calculate the A inverse. And so I give you 2 examples, 2 relatively simple examples to do. Right, so you should be able to find the inverse matrix for second or third order. Sorry, for the 2x2 or 3x3 matrix. For 4x4 is too complicated and takes too much time, so I'll just ignore that for now. But for the 2x2 matrix and 3x3 matrix, it's relatively easier to calculate by hand. So I think you need to know how to find the inverse matrix for a 2x2 and a 3x3 matrix. But everything is showing example here. Okay, so for the midterm review, what you need to do is to read chapter notes and to understand all the examples I use in the class, and also all the assignment questions, because the assignment questions are the examples I show in the class are very similar to the midterm questions you will see. And for the, yeah, as I said, there will be like 10 to 12 questions. And also I will post the midterm next Friday. And you'll have to submit midterm by Sunday. I mean, I'll make announcement for this, so please see my announcement.